In this video, I wanted to pick up where I left off in the last lecture, which was in the synchronized project, looking at synchronized blocks of code. I've shown you two examples in this code. The first example used the synchronized keyword on the invoking methods, and you can see that on the withdraw method. The alternative to a synchronized method is the synchronized statement. This requires us to pass some object instance to that statement, and in my example, in the deposit method, I passed the special keyword this, which means the current instance. In both these cases, a lock was acquired on my bank account instance. In the synchronized statement, this is explicitly declared. When I use the synchronized keyword on a method, the current instance is implicitly locked. But what does it mean when an object is locked? Every object instance in Java has a built-in intrinsic lock, also known as a monitor lock. A thread acquires a lock by executing a synchronized method on the instance or by using the instance as the parameter to a synchronized statement. A thread releases a lock when it exits from a synchronized block or method, even if it throws an exception. Only one thread at a time can acquire this lock, which prevents all other threads from accessing the instance's state until the lock is released. All other threads, which want access to the instance's state through synchronized code, will block and wait until they can acquire a lock. The synchronized statement is usually a better option in most circumstances, since it limits the scope of synchronization to the critical section of code. In other words, it gives you much more granular control over when you want other threads to block. In fact, it can give you more control than that. The synchronized block can use a different object on which to acquire its lock. This means that code accessing this bank account instance wouldn't have to block entirely. Let me explain this last point in some code. I'll add a private final string field to my bank account class and call it name. I'll include that in my constructor and I'll make it the first argument. I'll assign that to my local field. Now, I want a getter and a setter, so I'll generate those. I'll change the setter first to be synchronized because I don't want two threads to try to set the last name at the same time. I'll also add a println statement in this method, printing out the updated name. I'll output this .name here to confirm the name on the instance was properly set. I'll make my deposit method a synchronized method so I can demonstrate this easier. I'll add synchronized to the declaration and I'll comment out the synchronized block I had there. Getting back to the main method, I next need to change the line where I'm constructing my instance of bank account and include a name, and I'll use Tom to start. I'll also change one of these withdraw threads, let's say the third one. Here, I'll call my method to change the name on the bank account, so set name, and I'll pass Tim to that. Just to make sure we can really see who's being blocked, let's give the first two threads a 500 millisecond head start. Okay, so running this code, each time will be a little different. Sometimes I'll get the first withdraw thread before I see the talking to the teller statement, and sometimes I won't. But notice that the thread that updates the name on the account is blocked just the same as those updating the balance. All synchronized methods, regardless of what they are accessing or doing, can't run until they've acquired the monitor lock on the current instance. Now, I'll change my setName method to use a synchronized statement instead. I'll add the synchronized statement around both statements. And I'll again synchronize on this. Let's see if that helped the situation. I'll run the code a couple of times. You can see that updating the name is blocked until the conversation with the teller ends. Even though I'm using a synchronized block in my setName, I'm synchronizing on an instance, and that's going to get locked by our long-running deposit method. But I don't have to always synchronize on the current instance, the keyword this. In fact, in most instances, I won't want to synchronize on the current instance. Instead of this, I'll change the argument to this .name, so the field name. If I run this, I can see that the name gets updated before the deposit thread completed. In other words, it doesn't block for the deposit method thread. Why couldn't we do this with the synchronized statement for the deposit? Let's go back to that code and again remove the synchronized modifier and uncomment out that block. Now I'll change this to this dot balance. IntelliJ doesn't like that change, so let's see why. The message is telling me that required type is an object and we provided a double. An intrinsic lock or monitor is only available on an object, not on any of the primitive types. What if I created a local variable, a double wrapper type, and used that instead? I'll set this variable to the current value of balance. I'll change the argument to the synchronized statement and pass it my box balance. This code compiles, but IntelliJ does have a warning there. First, let's run this code. This seems to work, but we don't really have the right example to test this kind of change. Let's see what IntelliJ is warning us. You can see the statements, attempt to synchronize on an instance of a value-based class. That's a little vague. Essentially, we're attempting synchronization on a local variable. Box balance, in this case. Why is synchronization on a local variable a bad thing? Think about this for a second or two. Local variables are stored on the thread stack, so each thread would have its own copy of this box balance variable. The lock would be on the thread stack instance only. When you lock on a local variable, it's not going to be a shared lock, so it's useless. The only local variable that might work is a string, as long as it's been returned to the string pool. To simplify the rules for yourself, just don't use any local variable or method argument in this synchronized statement. Okay, that's fine, but how do we solve this problem then? What can we put in here besides this? You might remember that we talked about using big decimal when you're working on financial transactions, but let's just put that aside for now and keep this as a double. What now then? Well, you can create lock objects whose sole purpose is to manage locking for different fields. In my bank account class, I'll create two lock objects. I'll make them both private and final. And these can simply be type object. The first I'll call lock name and set that to a new object. The second one I'll call lock balance. Now I can go to the setName method and synchronize on lock name. I'll do the same thing in my deposit method, making that lock balance. Now, as you saw earlier, I didn't really need it for the name field, but this does make it a little clearer what the intentions are. It also removes any dependencies on these locks to your field types. Next, I'm going to add a method to this bank account method because the bank is running a promotional event. It's going to give $25 to anyone who deposits $5,000 or more. I'll make this private and void and call it add promo dollars. It takes a double for the deposit amount. I'll keep this code in its own method because I may change the promo quite a bit. If the amount is greater than or equal to 5,000, they qualify for this promotion. Here, I'll synchronize on the same lock as the other code that updates the balance, so I'll lock balance. I'll print that the depositor gets the promotional deposit, and I'll update the balance by $25. Since the add promo dollars method is going to be used in the deposit method, let me move it right below that method. I'll call this from the deposit method, putting it inside of the synchronized block. I'll call it as the last statement in this block, passing it the deposit amount. Let's think about this code for a minute. I'm in a synchronized block. I've got a lock on the lock balance object. My code then calls add promo dollars, which in turn tries to get a lock on lock balance. Does this mean my code is going to lock up in this scenario? Let's run it and see. When I run that, I can see everything is working normally and that I was able to get the promotional deposit with a final balance of $7,525. So how did that work? Why didn't the synchronized block in the add promo deposit wait on getting a lock? I said that once a thread acquires a lock, all other threads will block, which also require that lock. But in this scenario, one thread has acquired a lock and is calling another method. This is the same thread calling a different method, which is also trying to acquire the lock. Because these method calls are executed from the same thread, any nested calls which try to acquire the lock won't block because the current thread already has it. This feature is called reentrant synchronization. Without this, threads could block indefinitely. This concept is built into the Java language and it's based on the monitor mechanism. This is not to be confused with the reentrant block class, which I'll be covering, along with other locking topics in the next video. Since this video is getting long, I think it's time to move on to the next video, so I'll see you there.